Hello everyone, we're going to do an example problem using time learning models. What exactly is a time learning model? Well, a time learning model is a way to come up with numbers which will help you budget for how much quantity of labor you're going to have to pay for, and also what your labor cost is going to be for that quantity of labor. But it operates under a very real assumption. And that assumption is that as people do a task more and more and more, they become more proficient at it. And it makes sense. The first time that you do something, I don't care what it is, we'll go back to financial accounting. The first time you had to do journal entries, if you got 50 journal entries, it would probably take you quite a while to do them. The second homework assignment you had, you could have another 50 journal entries, but you'd be better at them. You'd get a little bit faster. It wouldn't take you nearly as long. By the 12th time you had to do a homework assignment that required you to do 50 journal entries, I'm willing to bet you'll be way faster than you were the first time. The same is true for manufacturing labor, like across any industry. If you're making a new product, if it's a new production process, if there's some kind of change to your production model, at first it's a learning curve. It's slower for your employees. They're figuring out what is the optimal way to do this. But as time goes on, they will have more experience to rely upon. They'll know all the tricks of the trade. They will get better and better and faster at what they do. So saying, okay, it's going to take this amount of hours to make a unit isn't the best way to go about things, because it assumes that your relationship between how many units you make and how long it's going to take is perfectly linear. Like, imagine it took you an hour to do something the first time, and then the second time you did it, it took you 59 minutes. Is it safe to assume that every successive time you perform that task, you're going to get a minute faster? And the answer is no, because if you did it 61 times, by that logic, starting at 60 for the first one and reducing by a minute each time, it would take you negative time to do the last one. No one learns at such a rate that it's possible that you can turn back time, like you're in a DeLorean, to get something done without it taking any time. Learning is always the biggest the first few times you do something. You'll make huge improvements the first few times you do something. And then after that, each successive time that you perform that task, you still improve, but it's not at such a large rate as it was before. Learning is exponential, but in this case, since we're considering time here, it's not exponential growth, it's exponential decay. You get much faster for the first few units, and then it kind of tapers off, so you don't have a straight line, you have a bit of a curve. And we're going to use that concept and some information here to come up with a time learning model to predict the total cumulative labor costs and average labor cost for Spadafora pools over here. They install in-ground natural setting hot tubs for private residences, like my wife wants in the backyard. The installation of these hot tubs requires the use of very skilled labor, and their management has noticed that historically more experienced workers successfully install hot tubs much quicker than newer employees. I don't think that's anything outside of the realm of what's realistic. People that have done things a lot of time become experts at it. Good old Malcolm Gladwell's 10,000 hour rule says if you have 10,000 hours of dedicated experience and practice at any one given thing, you will be an expert at it. The company's management is going to ask us to create a time learning model using an incremental method for the total labor cost of a brand new employee as he installs his first 8 hot tubs, if you will, during the period. What information do we have? Well, the first couple points are pretty easy. I'm going to start from the bottom of this table. For the first one, typically for us, the first time an employee has to put in one of these natural setting hot tubs, it takes that employee 100 hours. Our employees are waged employees that make $20 per hour, and then we have a learning curve of 80%. What that means, I will get to in just one second. But to make use of this information, we need to find our slope. And we find our slope by taking the natural log of our learning curve, and we divide that, in this case, by the natural log of 2. And I'm going to do that here. And to do that, we can use the ln function in Excel. So it just equals ln, open a parenthesis. We're looking for the learning curve, so I'm going to click that 80%. I'm going to close the parenthesis, I'm going to enter, and we come up with that crazy decimal. Here, I'm going to take the natural log of 2, so ln, open a parenthesis, type in 2, close the parenthesis, you get that number. And then when I divide the natural log of the learning curve by the natural log of the logarithm of 2 here, I'm going to come up with that decimal. And you're probably thinking to yourself, what in the hell does that mean? Natural log of our learning curve is 80%. We're finding here the natural log of 2. What that means, in less nerdy math terms, is every time the number of units that this worker has made has doubled, where the 2 comes from, the last unit that he or she makes is going to be done in 80% of the time than the unit was before production doubled. So we should have an 80% decrease in the time it takes between our first and our second unit as the worker learns. We should have another 80% decrease between our second and our fourth unit. That's when production doubles. So that should also, lead to an 80% decrease in the time it takes to perform that task. And then another production double will be from the 4th hot tub to the 8th hot tub. So that's another 80% decrease. And again, our relationship is not linear. It's not like each one is 80% faster. For next time, this employee would have, another decrease in expected time of labor between the 8th and 16th unit, and then 16th to 32nd unit, 32nd to 64th, 64th to 128th, 128th to 256. You get where I'm going with this. You're not getting 80% faster every unit. It takes, after a while, you have minimal improvement over time. But that is what our learning model is going to predict right here, is what we have to pay in labor costs if this particular worker gets so good at his job that he does it in 80% of the time that he did the last unit, every time the number of hot tubs he's put in private residences has doubled. And now we can just fill in our chart. We have the individual unit time for the xth unit, and the formula for that is right here. It is A times x to the power of b. Well, A is the constant. It's where it crosses our y-axis. It is how, in this case, how much time it took to produce the first unit. So that was 100 hours. We're going to multiply that by x, which is the number of units that this person has done, to the power of our slope, which is this crazy number we came in over here. And when I do that, I come up with 100. And that makes a perfect ton of sense, because we said the hours to produce the first unit would be 100. We're using the incremental method here, which means we are going to go through and figure out, as we were talking about before, how much time is saved on each unit individually. So after this first hot tub, it's 100 hours in total that we have to pay this employee to install hot tubs. Since this employee makes $20 an hour, if I multiply the total number of hours they've worked by 20 bucks, come up with $2,000. We're going to pay $2,000 in labor costs to pay this employee to install the first hot tub that they ever do for Spadafora pools. What is the average cost per unit now? Well, it's $2,000 for one unit. That's an average of 2,000. Just take your cumulative total labor cost and divide it by how many units you've made. For the second unit over here, we can use that same formula. A times x to the b power. A is our hours to produce the first unit, times x, this is our second unit now, to the power of our slope, which is negative 0.32 and a whole bunch of other stuff afterwards. And it comes out to 80. And that is a great point to check. Our theory says that every time the number of units this person has worked on doubles, that last unit they make should take 80% of the time as the unit did before production doubled. Did it take this worker 80% of the time to do the second unit that it did the first unit? You betcha it did. He's down to 80 hours for the second one. So now his cumulative total amount of labor would have been 100 hours for the first one, plus 80 hours for the second one. If we wanted this employee to install 2 hot tubs during the period, it, according to our estimate, would take 180 hours to do so. We are paying said employee $20 per hour, so if we pay this employee $20 per hour to make to work for 180 hours, our labor costs are $3,600, and now our average cost is $3,600 divided by 2, and that is $1,800 per hot tub that is installed. For the third unit, our A stays the same. It's still the number of hours it took our employee to make the first unit to install the first hot tub, which is 100, times X, we're up to our third hot tub being installed, to the power, good old caret from shift 6, of our slope. And that comes out to be 70.21 hours to put the third one in. So our employee had worked 180 hours to put the first 2 hot tubs in, a little over 70 for the third hot tub. This employee had worked 250.21 hours at this point, according to our projections. And if we pay that employee $20 per hour, it is going to cost Spadafora Pools a grand whopping total of $5,004.21 to pay that employee for the 250.21 hours that he'd worked. Now, what is our average cost per unit down to? Well, spent $5,004.21 to install 3 hot tubs, meaning we're paying on average $1,668.07 for labor for each hot tub that we install at this point. Let's go to the fourth hot tub. A times X, which is now 4, to the power of B, which is our slope, comes out to be 64 hours. Let's check here. Is this making sense? Again, our thing says that every time this person has doubled the number of hot tubs that they've installed, the last one they did should take 80% of the time as the one before production doubled. Well, 2 to 4 is a doubling. I mean, 2 times 2 is 4. So did this work out? Well, what was 80% of what we had before? Before it doubled, it took 80 hours. And if we multiply that by our 80% learning curve, it should take 64 hours for the employee to make the fourth hot tub, and indeed it did. So how many hours in total will our employee have worked, if we add the 250.21 we had before plus the 64 that it's taking to install the fourth hot tub? That's 314.21 hours to make 4 hot tubs in total at a rate of $20 per labor hour times the 314.21 hours. We would pay that employee $6,284.21 in total to install 4 hot tubs. And if we take our cumulative total labor cost and divide it by the number of units that our employee has installed, our average rate per hot tub is down to $1,571.05. Let's do the fifth, and I'm going to use absolute cell references in the fill handle, and we can really crank this table out. The individual time for a unit has been the same formula throughout. Our A never changes. Like A is always how long it took you to make the first unit. We want that to be absolute, so I'm going to make it absolute by hitting F4, or if you have to hold down the function key and hit F4 on your computer, that might work too. You know you're good when you got the dollar signs in there. We're good right now. Times X. And we want this number to change when we fill handle, because next time we want 6, next time after that we want 7, the time after that we want 8. Since we don't want it to change, do not make it absolute. To the power of our slope. And again, we want our slope to be exactly the same every time, because that is our slope. It does not change at all. So I'm going to make that absolute. And when I do that, I'm going to hit enter, and I get 59.56 hours. Well, here, let's do the cell reference, our formula for cumulative total labor hours, and it's always how many hours it took to make units up until that point, plus how long it took you to make your last unit. We don't want that to be absolute. We don't want to keep using the same numbers. This is always changing. Right? If you took 100 plus 80 is 180. And then up here we had 180 plus 70.21 was 250.21. We want these inputs to our formula here to keep sliding down. So I'm not going to make them absolute. I'm going to make it just like it is right now. I'm going to hit enter. Our cumulative total labor cost. How do we find that? Well, we multiply our cumulative total labor hours, and again we always used a different number here, whatever number it was for that particular level of production. So that doesn't want to be absolute. But our labor cost per hour never changes. So we want to make sure that we're always multiplying by 20. Again, I'm going to do that by hitting F4. I'm going to hit enter here. And then our average labor cost per unit. What did we do? 2,000 divided by 1 was 2,000. 3,600 divided by 2 was 1,800. 5,421 divided by 3 came out to 1,668. We want this to slide down every time. So I'm going to make this so it's always equal to our cumulative labor cost divided by the cumulative number of units. And that comes out in this case to $1,495.10. And now that I have everything set up correctly, we can make this go real fast. Fill handle in the corner all the way down the line. There we go. And one last time. All of our numbers have been inputted. Let's make sure that our logic is still holding true. I mean, we can always go and check. Our theory is when production doubles, this worker will do the last unit that he made in 80% of the time than before production had doubled. So 4 to 8 is the number of units he's installed, the number of hot tubs installed, doubling. So the 8th unit should take 80% of the time that it takes this employee to put in the 4th unit. Well, if I take the number of hours it took to put in the 4th unit and I multiply it by 80%, it should be equal to the amount of time it took him to put in the 8th unit. Is that true? It sure is. So now we have our incremental method time learning table all said and done. If this employee installs any number in here, we'll go with 8 units during the period, he will almost half the time it took him to put in the last time because he got better. Which means it wouldn't make sense to say, okay, it took 100 hours to put in the first one. We're just going to assume that on average it's always going to take 100 hours, or we're going to average just have to spend $2,000 in labor costs per unit. No, I mean, if we get a brand new employee to always put in every hot tub, that would be true. It probably wouldn't be too great for our reviews on Yelp having somebody brand new do everything that we did. More experienced employees are better at what they do, and this is definitely the case here. By the time this person has put in their 8th hot tub, they have figured stuff out, and they're much faster than they were. Because they're much faster, we don't have to pay as much. When we budget, in this case, if we knew we were going to make put in 8 hot tubs, we knew the aptitude of this employee, we knew all of this information we had, the number that we should be budgeting for labor cost during the period is $10,691.83. So that is the incremental method. It assumes that incrementally, the next unit that you make always is going to be, faster than the last one, and incrementally, every time the number of units you make doubles, the last unit you make is going to be take you 80% of the time as it did before stuff doubled. There is another way to go about this. It's incredibly similar, and it's the average time method. We have the same information here, but now instead of doing incremental time, we're going to do average time. Well, we can start off the same way. The natural log of the learning curve is equal to ln, the mathematical symbol for the natural log of our learning curve of 80%. The natural log of 2 is equal to the natural log of 2, so equals ln of 2. And then we find our slope by taking the log of the learning curve and dividing it by the log of 2. And we come up with negative 0.32198095. Let's go to the other one, make sure we have the same number. Yeah, we do. Okay, so that's what it should be. That's the slope of our learning curve. Now we can start off with our first set of numbers here. Formula doesn't change. It's still a times x to the b power. A is always how long it takes you to install the first hot tub, times x, the number of units you have put in. This is still the first one, so we're just going to click the 1 to the power of our slope. And it's 100, as it should be, because that's what it tells us is the amount of time it takes to produce the first unit. Our cumulative labor hours at this point will be 100. Our cumulative total labor cost will be the 100 hours our employee is going to take to put in the first hot tub times the $20 an hour that we're paying. And therefore, the average cost to put in a hot tub at this point, since we only put in one and it costs $2,000, will be $2,000 on average. For the second hot tub that we put in, we're going to use the same formula. And that is A times X to the B power. So our A, again, is still 100 hours for the first units. We're now on our second hot tub installation, so 2 is going to be our X, to the power of our slope. And there's 80 hours again. We're good. Now we have the difference. What we're saying here is not that the last unit that we took 80% of the time that it did before production doubled. What we're saying here is that every time production doubles, the amount of time that it takes to make any one given hot tub on average is going to drop by 80%. Well, if we're on our second installation and we need a number of cumulative hours right here that would make the average time to put in a hot tub 80, what would that have to be? Well, 2 times 80 is 160. We have, if we've installed 2 hot tubs and took a total of 160 hours, indeed, it took an average of 80 hours each to put in those hot tubs. And our learning curve still applies, but it's not to the last unit, it's to all units. Our average time is decreased to 80%. And now, for 160 hours, we multiply that by $20 per hour, and we get 3,200. If we divide that 3,200 by the 2 that we've put in, it is taking $1,600 of labor costs to install a hot tub on average if we put 2 units in during a period. For the third unit, A times X to the B power. A is still 100 times our X of 3 to the power of B, which we have right here. Our average time is 70.21, and as you'll see, this is the same numbers that we had before. It's still the individual time for we're still the same formula that we're coming in with, but now we're not having it be the individual time, we're having it be the average time. So if our employee is getting so much better at installing these hot tubs that after he puts 3 in, the average time is going to be 70.21 hours. That's 210.63 hours it's going to take this employee to put in 3 hot tubs. And at a rate of $20 per hour, the cumulative total labor cost is $4,212.62. So on average, if we got to spend a little over $4,200 to install 3 hot tubs, our average labor cost per unit is $1,404.21. And I want to start making cells absolute here so I can handle in the rest of the way. Our cumulative average time per unit is the same formula. So 100 times, we're up to our 4th unit, to the power of our slope, 64, which again is 80% of what 2 was, so production doubled. Our average time has dropped by 80% at that point. Our cumulative number of hours we're now finding by taking how many units we've installed times how long it takes us to put in each one of these on average, which is 64. It's 256 hours right there. Our cumulative labor cost is always going to be equal to what we had here times the labor cost per hour. I want to make that absolute, so I'm going to hit F4, so we're always going to use that 20. And our average labor cost is always equal to our cumulative total labor cost divided by how many units we've made. So after the 4th unit, our average time decreased by 80% when production doubled. We are averaging $1,280 per unit to install. And I got to go through and I got to make these absolute. You may do this yourself if you forget to put an absolute cell in or you realize you want one later. It's pretty simple to fix. Just go under your formula bar up on the top, click in the cell that you want, and you can just hit F4 and it'll change it. Now dollar signs are in there. I want this one to be absolute too, so I'm going to click right in the middle of it in my formula bar. I hit the function button on mine, hit F4. That's absolute now 2. There we go. And now when I fill handle, everything's going to be nice. Nope, no it's not. Why is it doing that? Because I didn't want that one to be absolute. See, professors make errors too. I'm even going to leave this in the video. I'm not editing it out. We're going to be good. I wanted this one to be absolute. There we go. And that looks much more realistic. And then here, fill handle in all the way down. And if we go with the average time assumption, not that the last unit we made takes 80% of the time that it did before production double, but that the average time to make any one given unit will be decreased by 80% whenever production doubles. You see that our average labor cost per unit is massively lower than it was under the incremental method, and it will always be true. So the average time methodology is applicable in situations for sure, and it's useful for budgeting because it gives you like this number that you can use on a master budget. You'll say if we make 75,000 units, this will be the average time we have, which is not something that's provided over here. You have to figure out your average time separately. The problem with it is in some situations it's unrealistic, and in this one that's definitely true. Like, I don't think anybody can get so proficient at installing hot tubs that they're basically reducing their average time at this just absolutely exponential rate. I mean, if we look at our numbers here and think about it this way, it took us 100 hours to do the first one, only 60 for the second one, down to 50 for this one. Last one is down to like 45, and then we got that guy in there in 41 hours. Like, it's just it's too fast of a growth rate. But if you're making a product that's made in just massive quantities, you're making thousands upon thousands, it is a pretty good way to go. I don't know if your learning curve will exactly be 80%, but because this is exponential and not linear, it flattens off severely at the end. Like, if it's not like, you know, this is, we can see right here, our increased time, or our time right here on average, is slowing down greatly. And if we keep doing this all the way till we got to like 8,000, it would be hundreds of a percent. So this methodology is a good way to go if you need this number for a master budget and you know you're making a whole mountain of units.